We know that the set of all solutions to a homogeneous system of linear equations is going to be a vector space. So now there is an algorithm that we can use to find a basis for that vector space, and we will start by just finding the set of all solutions to this equation. We will first find the reduced row echelon form for the matrix A here. Note that normally we would find the reduced row echelon form for the augmented matrix A and then vector B here. But because I know that this vector B is just going to be the zero vector, so the last column is just going to be all zero, so I don't really have to care. Now, to find the reduced row echelon form for this matrix, this doesn't look very human-friendly, so I'm just going to pull up my Python. Let me recycle my old code from here. So my matrix is going to be, let's see, -1, and then 1, 407, 1, and then 407. The second row is going to be 3 and then 1, and then -8, and then 2, and then let's see, 5. And the last row is going to be 2, and then 0, and then -6, and then -1, and 5. Okay, so this is the reduced row echelon form for the matrix that we have earlier. Let me go ahead and write this down. So the reduced row echelon form for this guy is going to be, let's see, 1, 0, -3, 0, 1, and then 0, 1, 1, 0, 8, and then 0, 0, 0, 1, -3. Notice that I have 3 leading ones here. So the corresponding variable, my x1, x2, and x4, they are going to be dependent variables, and the other two, let me actually kind of move this further down. The other two, which is my x3 and x5, this two is going to be free variables. So if I were to write out the solution, I'm gonna have that my x3 can be anything, and then my x5 can be anything. Now, if I were to look at x1 though, I can read out my first row as x1 minus 3x3 and then plus x5 equal to 0. So what that means is my x1 is going to equal to 3x3 and then minus x5. So then my x1 is going to be 3x3 minus x5. And from the second row, what I have is x2 plus x3 plus 8x5 equal to 0. So what that means is my x2 is going to equal, let's see, negative x3 and then minus 8x5. So my x2 is going to be negative x3 minus 8x5. And from the last equation, I will have that x4 minus 3x5 equal to 0. In other words, my x4 is going to be just 3x5. Now, let me actually move this a little further down. So my x4 is then going to be just 3x5. So what I'm going to do next is, I'm going to rewrite this general solution as a vector and then separate each of the free variables that I have. So from here, I can just rewrite this as a vector form. It's going to be just 3x3 minus x5 and then negative x3 minus 8x5. I'm going to have x3, 3x5, and then just x5 here. Now, let me actually rewrite this general solution in vector form by separating x3 and x5 from each other. So I'm gonna have, if I pull out all the x3 that I have, I'm gonna have 3x3, negative x3, and then just x3 and then 0, 0. Plus, if I group all the x5 together, I'm gonna have negative x5, and then minus 8x5, and then 0, and then 3x5, and then just x5. Notice that if I just add up these two vectors here, I'm gonna get the general solution that I have from earlier. But now, notice that I can pull out x3 from my first vector, and I can also pull out x5 from my second vector. So I can rewrite these two vectors as just 3, negative 1, 1, 0, 0 times x3 plus the second one would become negative 1, negative 8, 0, 3, 1 times x5. And what this means is I can write the general solution to this system of equations as just some vector times the free variable x3 plus another vector times a free variable x5. So what that means is I can think of these two vectors that I have, as just the basis, as just a basis for my vector space. Yeah. So whatever I have here is just a span of these two orange vectors here. So this two orange vector is gonna be a basis for my vector space. And let's also notice that the dimension of the solution to this system is going to be the same as the number of free variables. Notice that I have two free variables, which is x3 and x5 to begin with, and that will correspond to the number of bases that I have in the end as well.